So good afternoon, everyone. Welcome to our June mini school. We have already had two lectures by Dr. Sunandan Gangopadhyay. Yeah, and they were both very, very interesting. And today we have part 3 of his course on path integral methods in quantum mechanics and quantum field theory. Yeah. So Sunandan, people are
Okay.
here very keen to hear how the tale develops. Yeah.
Okay.
So
Okay. Thank you. Thank you.
maybe while
I'll,
you share screen, I quickly remind the participants to use the Q&A to ask questions at the bottom of your Zoom screen, or at the end of the talk, raise your hand and I will give you the right to ask the question directly. Yeah.
yes.
So Sunandan, please, you're most and
Yes.
welcome
Yes.
to
Thank you.
start.
Thank you,
Thank
Professor.
you very much.
So, yeah. So, are my slides visible now?
Yes, yes, yes. They are very visible and very clear
Okay.
to be read.
Okay. So, let me start today's lecture then. So, in the previous lecture, I will just make a brief recap of what I did in lecture 2. So, in lecture 2, what we studied was first I wrote down the form of the path integral representation of the transition amplitude from QITI to QFTF, and this was the form, the path integral representation. And the main thing that we did in the previous lecture was to look at time ordered correlation functions. So what I was trying to mention in the previous lecture that is the following, that if we have some operator insertions between these kets and bras, then what is their path integral form? So these matrix elements of these operators between these states. These are called operator insertions, matrix elements with some operator insertions between the respective states. And the first result that I showed to all of you was the following, that if we want to calculate the operator, the matrix element, or the following matrix element, which is this, then this can be written in this path integral form. This is a nice path integral representation. The right hand side, everything is are numbers. So I gave a proof of that result also. And the second result was the following, that if I want to compute the matrix element of the time ordered product of two operators, where I define the time ordering of two operators. So we have two position operators defined at two different times, and therefore we know that same operators defined at two different times, they do not commute, and therefore we need to time order properly. And the time ordering was defined in this way. And the result that we were talking about is the following. What happens, what is the matrix element of this time ordered product of two operators between these states? The ket is QITI and the final state is QFTF. And this result, we found that this is basically, this also has a representation in terms of path integral, and it can be written as path integral dq q1 q2 e to the power of, weighted by this e to the power of I by h bar action factor. And these q1s and q2s are, once again, these are numbers obviously, and q1 is basically q1 at time t1 and q2 is q2 at time t2. So we derived this result. And the next thing that I want to do today, or I probably started it a little bit in the previous lecture, but I still want to do it now. It is the topic is correlation function in definite states. So now I want to compute basically probability amplitude for a system in a state psi I h. So h basically denotes the Heisenberg representation. So I'm working in the Heisenberg representation, probability amplitude for a system in a state psi I h at time ti, to make a transition to a state psi f at time tf. And that probability amplitude, you can easily write it down. So this is the thing that we want to compute, ket psi I bra psi f. This is the object that is of interest now. So this object can be written in the following simple form. So what we do is we just introduce identities, and identity can be introduced in terms of the completeness relation. So I introduce an integral over dqf ket qftf bra qftf, and an integral over qi ket qi ti bra qi ti. So this object can be written in this form. Now, the first overlap, this is basically psi star f QFTF, and once again this is multiplied by this object, which is the overlap which we have been seeing so far, which is the overlap of QITI with QFTF, and this has a nice path integral representation that we have already developed, and so we can immediately write this QITI QFTF as path integral over Q e to the power of I by h bar action, I by h bar into action, and once again this particular overlap, the last piece, which is the overlap of ket psi I with bra QITI, is nothing but the wave function psi I at QITI. And now from this, once we have this step, from here we can straight away go to the next step. The next step is basically integral dqf dqy. So these wave functions are independent of these q's. These are these initial q's. So these are qi's, and this is the final q's, which is qf. So I can just pull it outside the path integral. So this is this. We can write this as integral over dqf dqy psi star f qftf psi I qi ti multiplied by this path integral, which is dq e to the power of I by h bar action. So where, as I have already mentioned, that the overlap of ket psi with bra qt is the wave function psi at qt. Now let me take another example. The next example, so this was the overlap of psi I with psi f. Now let us take the following operator insertion between these states. The states are psi I, the initial state, the state at time ti, and this is the final state, the state at time tf. And now I consider the following matrix element. This is the matrix element which we are now interested in. So this is the time ordered product of a string of operators. So these are some operators which are actually functions of the position operators. So I have some operator O1 hat, which is a function of Q hat at time T1, and then so on. So you will have O2 and so on, and this goes as till On. So I have another operator On hat, which is a function of Q hat at Tn. So I have a string of operators, and there, since the operators are defined at different times, therefore we obviously need time ordering. And I considered the matrix element of this operator between the states psi I and psi f. So the way to proceed is once again the same. We have to introduce completeness relations, which are basically identity operators. So I introduce the same completeness relation between QFTF and bra QFTF, integral over QF, and 1 over QI. And if you do that, then this expression will boil down to the following expression. So now I will have an expression where you have this, which is nothing but psi star QFTF, and then the matrix element of the operator between the position states, which are QITI and QFTF, and then once again this multiplied by this term, which is the wave function at QITI. So I can write down this full object as an integral over dqf dqy psi star f at QFTF, and this object bra QFTF, the time ordered product of these string of operators ket QITI, this can be written in a path integral form, and the path integral form is path integral over dq O1 at Q1 T1 multiplied by On at Qn Tn. I have missed a bracket here. I just need to put some bracket. So there will be a bracket here. So that's fine. So the important thing to notice, I would like to stress this fact that now everything in this expression are all the things appearing in this expression are ordinary numbers. They are C numbers. They are no longer operators. So in path integrals, the basic takeaway lesson is that you need to work with, you are working only with numbers. So this is a simplification. You don't need to worry about commutation relations anymore. So you're not working with operators. So this particular expression that we have, this can be written as a path integral, and the path integral is over these functions weighted by this action factor, and then you have a wave function. And once again, you can pull this wave function, initial wave function outside, and you can write this expression in the following form. You can write it as an integral over QF and QI psi star f as a function of QF and TF, and psi I as a function of QITI, and then multiplied by a path integral this. So the matrix element of this operator between this as the initial state and this as the final state is given by the following expression. You will understand in a moment why we are actually working all these things out. The next thing that we want to calculate are expectation values. So what we shall do is a very simple thing. Instead of taking this to be psi f, we shall now put this to be psi I. So that basically means that we are after the matrix element, or we are after the matrix element of this operator between the same states. That means we are after expectation values of this operator. So let us compute the expectation value of this time ordered product of this string of operators. We already have the expression here. We have derived it. Just instead of f, we need to replace f by I and nothing else. But not these. These we will not replace by I, because the completeness relations that we have introduced is 1 over QITI and 1 over QFTF. So if you do that, the expectation value of this string of operators between the state psi I and this bra psi I, between this state, is basically given by this expression. So now the only change in the expression is it will be an integral over QF and QI, and then the integrand will be psi I star at QFTF. So this is the initial wave function at the initial wave function at the position QFTF, and the initial wave function at the position QITI, multiplied by the path integral expression, which was already there. So this actually gives the expectation value of this time ordered product of the string of operators. And this result is true when the initial states psi I, between which we are taking the expectation value, between the states psi I are normalized. So this result is valid only when get psi I bra psi I is equal to 1. For states which are not normalized, that is get psi I and bra psi I is not equal to 1, then the result for this expectation value, now I have just replaced, I've put in this operator inside some these angular brackets. So this means the same thing. It basically means this object. So we are taking expectation value in this state. So I've introduced a shorthand for that. So in that case, when the psi i's are not normalized, then the expectation value of this string of operators, the time ordered product of this string of operators, is given by the expression this divided by the overlap of psi I by psi I. So when they are not normalized. So these objects, so the objects that we have been computing from lecture 2 and we have been discussing today. So let me just go back. So the first object that we computed was this, and I denoted this result by this A. This is one of the first results. So this is an operator insertion, and I computed a matrix element. Then the next result was this one, which is the matrix element of a time ordered product of two operators between these position states. And then we went on to calculate the matrix elements of these operators between definite states. These are basically called correlation functions. So we have been computing correlation functions between position states, correlation functions of operators between position states, as well as correlation functions of operators between definite state gates. So these are the things that we have been computing. These are important. As you know, correlation functions are very important in quantum mechanics. You have a lot of information stored in them. So now the next question that we ask is that, is there a generating function or functional for these correlation functions? So we want to write down a generating functional for these correlation functions. What do I mean by that? This generating functional is a functional from which, by functionally differentiating, you can actually obtain all these correlation functions. So it is something like that we have already studied in theory of special functions in mathematical methods, that there we have generating function for Hermite polynomials. So you write down some function, and from that function you can actually obtain all the Hermite polynomials. So here also it is something similar to that generating function, but in this case it is called generating functional. So this is some functional from which we can actually generate all the correlation functions that we have been talking about. So how to construct, so the question that we are now trying to address is how to construct a generating functional. So I shall tell you briefly some steps, some very simple steps by which if you follow these steps, you will be able to obtain the generating functional very easily. So what is the first step? Step one is, let us first define a modified action of the form this. So we define an action S, which is a functional of Qt and some other function Jt. So I have not written, so let me just write. So this J is also a function of T. So we define a modified action of the form, which is a functional of Qt and Jt in the following form. So S is basically equal to S naught Qt plus integral Ti to Tf Jt Qt dt. So this S naught is basically the action functional where there is no source. So the definition that we have put forward, which is S is equal to S naught plus this integral. So in this definition, if we just put J to be equal to 0, so S functional of Qt comma 0, by construction, you can see that when we put J is equal to 0, this term will vanish and we will have S Qt comma 0 to be equal to just S naught Qt, functional of Qt, where S naught Qt gives the dynamics of the system. So this is the first step in the construction of the generating functional. We now go to the second step. We now define the following object. So far, if you remember at the beginning of today's lecture, we computed the overlap of psi I with ket psi I with bra psi I. But now I define a new object, which is the overlap. And by the way, this J is called an external source. So in quantum mechanics, it is not, there also we call external source, but this external source terminology is very familiar in field theories, in quantum field theories. So this is an external source. Good. So now let me just proceed. So step 2, we now define the following object, which is the overlap of ket psi I with bra psi I, and I put a suffix J. So this means that this overlap is basically defined in the presence of the source J. And I define it in the following way. This is some constant n, then it is an integral over qf qi psi I star qf tf psi I qi ti multiplied by the path integral dq e to the power of I by h bar and the full action. This is the action in the presence of the source J, which we have defined in step 1. And if you notice carefully, this object psi ket psi I bra psi I in the presence of this source J, this object has been defined in such a way. So this definition is very close in spirit to the form that we obtained for the overlap psi I psi I. So this was the form of the overlap that we obtained earlier. So you can just get the overlap of psi I by just replacing f by I here, and you will get the answer. So the answer that we got here, we just once again define the same object in the presence of the source in the same way, but just by replacing the action S, which was a functional of Q only there. So now the action is a functional of Q and the source, external source J. So this is a definition. So once again, you will see that if you put J to be equal to 0, so that will give us overlap of ket psi I with bra psi I. And if you put J to be equal to 0, you will get back the previous expression that I've been talking about. So if in the limit of J being equal to 0, this SQJ, we have seen that it goes to S naught Q. So you recovered the earlier expression. So everything is fine. The definition is consistent with what we got earlier. So this is the second step. Now let us come to the third step. The third step is we need to functionally differentiate this object that we have defined with respect to the external source J. So this is the object that we have defined, and we now functionally differentiate, not ordinary differentiation, but functional differentiation I have not defined what functional differentiation is, but I can do it in the question hour session. I have a slide for that. So it will be a very short primer for functional differentiation. So if you functionally differentiate this object with respect to the external source at time t1, and whatever answer you get, if you set that answer and if you evaluate that functional derivative at j is equal to 0, then what will you get is the following. So delta jt1 of this object evaluated at j is equal to 0 will give you the following thing. So you just go back to this expression. You notice that you are functionally differentiating with respect to the external source. There is no j sitting over here, so this object will remain untouched. So let me go back to this expression. So there is no j sitting over here in psi I star this and this. So this object will remain untouched when you functionally differentiate with respect to j. Only j is sitting sitting in this expression, which is a path integral over q e to the power of I by h bar s qj. So this term will contribute when you functionally differentiate with respect to the external source. So if you differentiate, the answer that you will get is, so this remains untouched, then path integral over the q I by h bar, it pulls down the factor of I by h bar from the exponent, and then delta sqj with respect to delta j at time t1, because you are differentiating functionally with respect to the external source at the time t1. So you have a t1 over here, and then e to the power of I by h bar, this j is equal to 0. You should remember that functional differentiation follows all the rules of ordinary differentiation. So you just differentiate it in the usual way, but there are some subtleties that I shall talk about later. So you get this expression, and now the task that remains is to evaluate this particular object. And sqj, you already know what sqj is. So sqj is basically, or s naught at q plus integral over from time ti to tf jt qt dt. So integral over jt qt dt is basically a functional of j. So you are differentiating that functional with respect to the external source j at time t1, and if you do that, it will basically give you a factor of qt1. So why it should give a factor of qt1? Basically, what I am saying is that the result of this result, this particular thing, is nothing but q at t1. So I'm replacing this by this. We can easily prove why this is equal to this. If you are get stuck, I can clarify this point later. So the result of this is basically equal to this. And now you have to set j is equal to, after completing the functional differentiation, we have to set j is equal to 0. And if we set j is equal to 0, what we will land up is the following expression. This is the expression that we will land up to. But this expression, we have already seen that it is nothing but the matrix element of the operator, of the position operator q hat at time ti between the state psi I and psi, in the state psi I. So it is basically the expectation value of this operator defined at time t1 in the state psi I, where t1 is a time which lies between ti and tf. So what we have seen is that, so the important takeaway lesson of that we should take from this result is the following. If you functionally differentiate this object that we have defined with respect to j once, then you will get this, which is nothing but a correlation function. You can think of this about like a correlation function, because this is basically there are here it is a single operator, so it is trivial in that sense, but it is basically the expectation value of an operator at time t1 in the state psi I. So you can see that this object that we have defined gets psi I, bra psi I in the presence of the source j. If you functionally differentiate this quantity, it will give you expectation values. Let us proceed. If we carry out this exercise once more, so we are now functionally differentiating this object 2 times with respect to the external source. So let us carry this task twice. So now it is del 2 this object, del jt1, del j2, j at t2, and evaluate this at j is equal to 0. If you carry this out 2 times and then set j to be equal to 0, the result that you will get is the following. It will be this normalization constant integral over qf qi, these ordinary objects. Here there are no j's, so you don't need to worry about these. And then the differentiation will touch the path integral, this integral over path integral over q, because here lies the j in the action. So when you differentiate, it will pull out a factor of I by h bar whole square, and then you will have delta s delta j t1 delta s delta j t2 multiplied by e to the power of I by h bar s, and then you evaluate this at j is equal to 0. You have already calculated, we have already mentioned that this object and this object that you have here is nothing but q at t1, q at t2, and therefore this particular expression you can write it down as I by h bar whole square. It is the expectation value of the time ordered product of two operators between in the state psi I. Why? Because when we started the lecture, if you remember carefully, we actually proved that the expectation value of this operator between this state is basically equal to this expression. And therefore now what we have shown is that if we functionally differentiate ket psi I bra psi I overlap with in the presence of the source j with respect to the external source j, and set it to be and set the functional differentiation derivative to 0, then we will land up to this expression. But this expression is nothing but the expectation value of the time ordered product of these two operators. So once again we can see that the lesson is that if you if you carry this process out, that is functionally differentiate that object with respect to the external source multiple times, and then set the functional derivatives to j is equal to 0, then you will recover all the correlation functions. So that object, that ket psi I bra psi I overlap evaluated at j is equal to in the presence of the external source j, that object is basically like a generating functional. It is a generator of all the correlation functions. If you functionally differentiate that object with respect to the external source multiple times and set the results to at j is equal to 0, evaluate the results at j is equal to 0, it will give you the correlation functions. This is the basic lesson that I wanted to tell you. So the final result, if you write this object, that is now you have a string of n j operators defined at time t1s and tn. So you are now functionally differentiating this object n times with respect to the external source and setting the derivative j is equal to 0. Then that object is basically equal to nothing but, apart from this factor, it is basically the expectation value of the time ordered product of this string of operators in the state psi I. Right? So it has, so the lesson is that you have differentiated this and you have obtained the, so differentiation of this leads to the correlation function. So you can now say that this is basically the generating functional of correlation functions. So the general result now, this particular object I'm writing in a shorthand notation. So I'm writing this in angular brackets, which basically means that it is this thing that is basically equal to minus I h bar whole to the power of n times this factor. So I've taken this factor on the other side of the equation, that gives you minus I h bar whole to the power of n, and then this divided by psi I overlap in the presence of the external source. Why is this factor necessary? As I mentioned earlier, this factor is necessary because of normalization reasons. If psi I is normalized, then there is no problem. If psi I is not normalized, then you just divide by this factor, and you already have this factor. And then after calculating everything, you just set it to j is equal to 0. So that will give you the expectation value of this time ordered product of this string of operators. So now with this background, we are now calling this object psi I ket psi I bra psi I overlap in the presence of the external source as something proportional to z of j, where this z, we are introducing a new notation, this z, which is a functional of this external source j. It is called the generating functional for the time ordered correlation functions. So this is the generating functional. which will actually generate all the correlation functions. And we are after the correlation function because correlation functions are something very important in both quantum mechanics as well as in quantum field theory. So this generating functional Zj, the formalism that I just now talked about, this actually leads to the concept of vacuum functional. So let us see what do we mean by vacuum functional. An object of great interest in not in quantum mechanics, or I should say in quantum. So let me just replace this like this and go here and write this as okay. So an object of great interest in quantum field theory is the vacuum to vacuum transition amplitude in the presence of an external source. So this is an object of extreme importance, and you will because of obvious reasons, because this is an object from which you can actually derive all the correlation functions in quantum field theory. And the 2 point for a free quantum field theory, for example, if you take a free scalar field theory, if you compute the 2-point correlation function, that is basically that basically corresponds to the propagator of the theory. So that is why these correlation functions are very important. And for a free theory, the higher point functions for a real scalar field theory, if you want to compute a 4-point correlation function, that you can write as a product of 2-point correlation functions. So, and the 2-point correlation function, as I've already mentioned, is basically a propagator. So let us see how can we go, how can we go to this, or what do we mean by this vacuum functional? So this is basically the vacuum transition amplitude in the present, vacuum to vacuum transition amplitude in the presence of an external source. So it is, so physically, what do we mean by this vacuum to vacuum transition amplitude? So you can imagine in this way that in the extreme, in the infinite past, there was vacuum, and then in the infinite future also there is vacuum, and in between in some time interval there is some external source which is causing the interactions between some objects, for example particles or fields. There is some field interaction that is taking place in some intermediate time. In the extreme past, there was infinite past, there was no interaction. In the infinite future, there is no interaction. And so you want to compute the transition amplitude of a vacuum which was there in the infinite past to a vacuum which is there in the infinite future. So and in the presence of an external source, and this source basically defines some sort of an interaction. So you are switching off, switching on an external source in between some time interval. So this is an object which is of utmost importance in both quantum mechanics as well as quantum field theory. So let us see how we can construct such an object. So let us write down the following object, which is Qt, ket Qt, and Q prime T prime overlap in the presence of an external source J. And this object, you can write it down in the following way. We have already, if you remember, we had already defined an object like ket psi I bra psi I in the presence of the source J, and it was defined in the following way. Let me just go back to the previous slide, which was step 2 basically. So if you go back to step 2, you will see that the ket psi I bra psi I overlap in the presence of the external source. This was defined in the following way. There was a path integral e to the power of I by h bar action sqj, where in step 1 sqj was defined as s naught plus this integral. So let me now come back to this expression, which is the overlap of Qt with Q prime T prime. Obviously, T prime is a time which is greater than capital T this time, and you can write it as some path integral form. So previously we have been talking about this object where there was no source, but now we are talking about this object in the presence of an external source J, and you can just define it in an analogous way as we have already done earlier in step 2. It is some normalization constant, path integral over Q. These are the boundary conditions over the path integral measure. So it tells you that we are going from, so this will be, sorry, so this will be, there is a small error here. want to correct it. This will not be there, and this will not be there. Let me just correct it. Sorry for that. So this will be qt, and this will be q prime and t prime. Okay, so now everything is fine. So this is path integral. These are the boundary conditions on the path integral on the all possible paths in the configuration space. And then you have the weight factor, which is e to the power of I by h bar integral I by h bar action, but the action in the presence of the external source, because now we are computing this overlap in the presence of the source j. So e to the power of I by h bar integral t to t prime dt. This is the usual action L q q dot plus jt qt, right? So this is basically this object in the presence of the external source j. But now I want to write down this object in a different way. So I want to introduce completeness relations. So I want to introduce identity operators, and I do that in the following way. I introduce an identity operator by introducing an integral over q prime t prime bra q prime t prime, and then I want to introduce another integral over q, which is qt and bra qt. And if I do that, I will get this expression. Now please look at this this diagram carefully. So if you see this diagram carefully, then you will find that there are three time zones. So one is from -infinity to capital T, where and then from capital T to small t. So in this region, this full region, in fact, the j external source j is equal to 0. The external source is switched on in the time interval small t to t prime. So you will see that this interval, there is j not equal to 0, and therefore this particular overlap from qt to q prime t prime, this is in the presence of the external source j. And once again from t prime or from small t prime to capital T prime, this particular, and away to infinity, this particular zone, there is no external source. So this particular overlap from T prime to capital T prime, there is no source. This particular interval from T to T prime, there is external source, so J is there. And from capital T to small t, there is no external source, so there is no need of putting J. And obviously T prime is greater than small t prime is greater than small t, and capital T prime is also greater than capital T, and both T prime and small t prime and small t lie between capital T and capital T prime. So what we now want to do, we are after the following object, the vacuum to vacuum transition amplitude. So we want to isolate the ground state. The vacuum is the ground state, and the way we can do it is by rotating the time axis. So what we do is, you will see that this is the time axis. So this is the direction of time. We are now rotating the time axis in the clockwise direction by an angle delta. So this is the rotation, and the time axis is now this particular thing. So we have rotated this by an angle delta. And let us look at this object. So our main idea is to isolate the ground state. So in this overlap, one of the first overlap that appeared on the right hand side was this. So let us calculate this object first. So this object q prime t prime bra capital Q prime t prime is basically can be written in the following way. You can move on from the Heisenberg representation to the Schrodinger representation by writing these position states in terms of these Hamiltonian operators in this way, evolution operators. And obviously, as I mentioned earlier in my earlier lecture, that h hat is time independent. So you can write this in the following way. And now this is the first step. The second step is we introduce eigenstates of the Hamiltonian of this Hamiltonian operator. If you introduce the eigenstates of Hamiltonian operator, that is h hat acting on ktem is equal to em ktem. And what we have introduced here is nothing but a completeness relation. This is an identity operator involving the eigenstates of the Hamiltonian operator. So I've introduced an identity here and identity here. If you do that, you just pull this summation over m and n outside, and the resulting expression will be this. H hat acting on this m will give you the eigenvalue em, and similarly h hat acting on this n will give you the eigenvalue en. So the final expression that we will get is the following. You will have an overlap of bra m and ket n, and that since the eigenstates are orthogonal, the eigenstates of the Hamiltonian operator are orthogonal, you can replace this by a Kronecker delta, delta Mn, and this Kronecker delta will kill one of the sums here, and you will ultimately land up to this single sum, and this will be the expression. So this particular object in the absence of the source is nothing but this, where phi m at function of q prime is basically the overlap of m with q prime. This is the energy eigenfunction. So we have computed one of the objects in this expression, which is this. If you do the same, if you carry out the same exercise for this object, you can straight away write down the expression, and the expression will be this. You just carry out the same exercise, you will get this expression. And now what you do is you just plug in these expressions in the above expression, and if you plug in these two expressions, the result for this overlap qt with q prime t prime in the presence of the external source j will be nothing but, you just plug in all the expressions, you will get this. This is the big expression that you will get. We have not computed this, which is the overlap of qt with q prime t prime in the presence of the source, external source j. Now let us take the limit capital T prime going to, so this is the time which is greater than capital T. So we are taking this time to the infinite future. So we take capital T prime to infinity e to the power of minus I delta. So you can see that if you take this limit, it is basically equivalent to rotating the time axis in the clockwise direction. You take this limit and take capital T to be equal to minus infinity e to the power of minus I delta, where delta lies between, it is less than or equal to pi by 2. So if you do that, you will immediately see that if you set capital T prime to be equal to this thing and capital T to be equal to this thing in this expression that we have derived, it will actually kill all the higher energy eigenvalues. The leading term that will remain in this expression will be the ground state. The leading contribution will come from the ground state energy. All the higher energies, they will just vanish off. They will not contribute. This is you can easily see from this expression. If you just put in the limits that we have used, you just put in t prime to be equal to this and capital to be equal to this. The way we have chosen this is to introduce a damping factor, and you will see that since E1, E2, and so on are all greater than E0, therefore the leading contribution will come from E0, and all the E1, the contributions coming from E1, E2, and so on, they will be smaller than the contribution coming from the ground state. So the rotation of the time axis in this particular way in a clockwise direction is equivalent to isolating the ground state. So this expression that we have been after in the limit in these following limits actually boils down to the following expression. So what has happened is the following. In this, there was a summation over m and summation over n, but now you will see that only the ground state wave function contributes, because all these higher terms, when m is equal to 1, 2, and so on, they have died. They are not there in the expression. So you only have phi naught q prime, phi star naught q small q prime, and so on. So you will have this expression. And now the interesting thing is that this particular phi naught q prime, and in this expression you will see that there is a function which is phi naught over a function of capital Q prime and phi naught star as a function of capital Q, and the integrations are over small q and q prime. So what is happening is that you can just pull these two factors out because they are independent of the integration. You can also pull this out of the integral, and you can write this expression in the following way: phi naught q capital Q prime, phi naught star capital Q e to the power of this factor times this integral. These factors that you have, you cannot pull out of the integral because these are functions of q prime and q. So, and the integral is over q and q prime, so you cannot pull out these factors. So this is basically the integrand. The other factors are independent of small q and small q prime, so you can pull it out of the integral. And therefore, now this particular integral, you can take these factors on the other side. You can write this particular thing as limit. These limits that we have taken, it is basically the left hand side is equal to this object divided by this object. These are some numbers. So this left hand side, this particular thing is basically nothing but it is proportional to this object, which is the overlap of capital Q at time capital T with capital Q prime at time capital T prime in the presence of an external source. So this particular object is basically proportional to this particular object in the particular limit this. But the question is, what is the left hand side? The left hand side, if you look at carefully, it is basically the expectation value or the vacuum to vacuum transition. So this was the transition amplitude, right? This was QT with Q prime T prime in the presence of an external source. This is the vacuum to vacuum transition amplitude. Why vacuum to vacuum? Because this is like an expectation value. If you look at carefully, this is the transition amplitude from QT to Q prime T prime in the presence of source. But now you are computing this transition amplitude between these wave functions. This is the ground state wave function at Q and the ground state wave function complex conjugated at Q prime. So this is like an expectation value in the ground state of this object. And therefore, this particular object that we have, this is called the vacuum to vacuum transition amplitude in the presence of an external source. This full object is given a shorthand notation. It is written in the following way: 0, minus infinity to 0, plus infinity, because we have taken the limits capital T prime to plus infinity and capital T to be equal to minus infinity, and the full object is in the presence of an external source. So this is the vacuum to vacuum transition amplitude in the presence of the external source. Also, it is known as the ground state expectation value of the transition amplitude in the presence of an external source JT. So this is the ground state expectation value, because as I mentioned, because these are the ground state, and expectation value because of the transition amplitude. This is the transition amplitude in the presence of an external source. Therefore, this is the expectation value of this object in the presence of an external source. And once again, I introduce another notation. I have called this particular expression to be equal to this. I have defined this expression to be equal to this. Now I am just saying that this particular thing is nothing but Z of J. So Z of J is proportional to this thing, which is 0, minus infinity, and bra 0, plus infinity overlap in the presence of an external source J. But this particular object, as we have seen, is proportional to this object, which is the overlap of capital Q, T with capital Q prime at T prime in the presence of an external source J, with the following limits for capital T and capital T prime. Therefore, Zj is proportional to this object, but this object has a path integral representation. Therefore, Zj is nothing but, apart from some normalization factor, limit T going to this, capital T prime going to this, it is a path integral over Qt e to the power of I by h bar integral from T to T prime dt L plus jq. So we have now the expression for the vacuum to vacuum transition amplitude in the presence of an external source, or this is the generating functional, as we shall see now. This is called Z of J. This is the generating functional because this is functional of the external source J. And there, since we have taken the limits t to be equal to this and t prime to be equal to this, you can actually remove this limit completely. You can remove this thing from here and just write this to be equal to, and this to be equal to. You can just come here. You can write this to be equal to. I'm not finding the pointer now. Where is the pointer? I got the pointer. So you can replace this by minus infinity and replace this by plus infinity. So what we have now is the vacuum to vacuum transition amplitude, which is a functional of the external source J, Z of J, is basically nothing but a path integral over Q e to the power of I by h bar integral minus infinity to plus infinity dt of the Lagrangian L plus external source J times Q. So this is the general expression of a generating functional, which we have already seen that the basic concept of the generating functional is the following. It is an object from which you can, obtain all the correlation functions by just functionally differentiating with respect to the external source j and then setting the result to j is equal to 0. So that is why this object is very crucial. What we shall now do is we shall now, so this expression was obtained in the quantum mechanical scenario. What we shall now do is we shall straight away now move to quantum field theory and just write down, generalize this expression for fields. So when we do quantum field theory, all these position operators, these get replaced by fields. Basically, position operators gets replaced by field operators since we are talking about field theory. But since now here we are doing a path integral formulation of quantum field theory, therefore we no longer have fields, but you just have some functions, ordinary functions. That is the advantage of working with path integrals, that you just need to replace, you just need to work with ordinary functions. There is no operator sitting in path integrals. So what we do in quantum field theory, you just generalize the quantum mechanical result that we have obtained for the generating functional in case of fields. So we write, in case of a field theory, the generating functional in the presence of an external source can be written as a path integral over fields e to the power of I by h bar s naught, which is the functional of the field, plus integral over jx phi x d4x. So now we are considering 3+1 dimensional quantum field theory. So it is a 3+1 dimensional quantum field theory. So that is why we have an integral over d4x, and this is a field theory in flat spacetime, in Minkowski spacetime. Therefore, the invariant Lorentz invariant volume measure is basically d4x. So you will see that this expression has been written directly from the quantum mechanical expression that we have derived. It was z of j path integral over q e to the power of I by h bar integral minus infinity to plus infinity dt L plus jq. Now we have replaced q by phi, and this integral is from minus infinity to plus infinity, and this dt by d4x, and this thing that we have over here, this is the action, the free field action, and this term that we have here is jq. Here it is jx times phi of x multiplied by integral multiplied by d4x, and there is an integral over d4x. And s naught phi is basically, if we work with a real scalar field theory, it is nothing but s naught phi is basically equal to integral d4x times half del mu phi minus m square phi square. And if you have you can put in an interaction also for so this s naught phi can be the action for a real scalar field theory, free scalar field theory, or a interacting scalar field theory. I have just put in a 5-foot interaction over here. You can just avoid this to start with. So if you just set this term to 0, then it will be the action for a real scalar free field theory, and the action for that is just the first two terms. So s naught phi is given by this expression. And in case of lambda phi 4 theory, we have this. So this is a self-interacting theory. You will have this interaction term sitting over here. And our main, so once we have this generating functional in hand, so the generating functional that we have written, this generating functional for field theory in hand, you can once again go ahead and compute all the correlation functions step by step, by functionally differentiating with respect to the external source j. So now, with this setup that we have established now, let me just show you certain results in functional integration. I will just show you a couple of results and then stop for today, because I think that would be a nice place to stop for today. So let us now just make a brief digression and see some results in functional integration. And let us assume that we are working with bosonic variables. The first result in functional integration that we need to know is the following result. The path is a functional integral over phi x e to the power of minus half integral from minus infinity to plus infinity d4x phi x operator. This is an operator a hat phi x. It is nothing but equal to the determinant of this operator to the power of minus half. So this is the first result. It is, you can you may ask, how do you get this result? It is very simple. You just think of the ordinary Gaussian integral. So this is, if you look at this integral, this functional integral very carefully, you will see that there are two factors. There's phi and phi. So it is a Gaussian functional integral because there is a damping factor, e to the power of minus is sitting over here. So it is Gaussian. And on top of that, why it is Gaussian? Because there is a minus and there are two factors of phi. So it is a quadratic. It is a quadratic in phi. So that is why it is a Gaussian functional integral. And you just go back and recall the result for the ordinary Gaussian integral. In case of ordinary Gaussian integral, you just have the result is basically square root of pi by a. So if you have a x square integral e to the power of minus a x square integral over dx e to the power of minus ax square dx. I showed you this result earlier in the previous lecture. It is basically equal to pi square root of pi by a with the constraint that real part of a should be greater than 0. So a can be complex, but the only constant is that the real part of that complex number should be greater than or equal to 0. That will make it make the integral converge. That is why it is called a Gaussian integral. So in the functional generalization of that result is nothing but this result. So you, instead of a ordinary integral, you now have a very complicated thing, which is a functional of phi, and you integrate over all possible functions. So this is a functional integral, which is an integral over all possible functions, and you have an operator sitting here. The result is basically determinant of s square. So it is once again the determinant of that operator goes in the denominator. This is something very important for bosonic variables. And what you may ask, what do you mean by a determinant of an operator? It is basically it is called a functional determinant. So this is also something that we need to know how to evaluate functional determinants. Basically, you can think of an operator as a matrix. Just think of a matrix operator, and if I ask you to calculate the determinant of that operator, what will you do? You will just calculate the eigenvalues of that matrix, and the determinant of that matrix is basically the product of the eigenvalues. In this case also, you do the same thing. You just need to obtain the eigenfunctions of this operator. Once you know the eigenfunctions of this operator, you know the eigenvalues of this operator, and then the determinant of this operator is just the product of the eigenvalues. So these are called functional determinants in the literature. So this is the first result that I want to show, and the second result that I want to show before I stop is the following result, which is a functional integral. Once again, this is a Gaussian functional integral. It is a functional integral over phi e to the power of minus integral minus infinity to plus infinity d4x of half phi x. This is an operator a phi x plus b function of x. This is an ordinary function, which is a known function, say, times phi x plus some known function c of x. And the result for this functional integral is once again determinant of a square to the power of minus half times e to the power of integral d4x of half dx a inverse dx minus cx. And in the next lecture, we shall see a proof of this second result. I think it is a good place for us to stop here for today. So why I am showing why I need these two results is very simple. For the real scalar field theory, for the free scalar field theory, I will just switch off this term for the time being and just put in the form of this action in this generating functional, right? I will just put in half del mu phi minus n square phi square, this thing over here, and then try to calculate this generating functional in the presence of the external source. And in order to calculate this object, I need the results. I need result 1 and result 2. In particular, I need actually result 2 uses result 1. So this result actually comes from result 1 that I have shown. And in the next lecture, what I shall do is that in order to evaluate Zj, I will use result 2 directly, and that will give us the value, the expression for the generating functional for in the presence of the external source J for the real scalar free field theory. And once we have the expression for the generating functional, all the endpoint functions can be calculated, and that will give rise to the propagator. The 2-point function will give you the propagator for the real scalar field theory, which is a very important object for quantum field theory. The propagator is the basic building block of a quantum field theory. So we need to know how to calculate propagators. For given any free field theory, we need to know how to calculate the propagator of that theory. Be it a real scalar field theory, be it a complex scalar field theory, be it some fermionic free field theory from Dirac free field theory, be it the electromagnetic free field theory, which is a abelian gauge theory, be it some non-abelian gauge theory. We need to know how to calculate propagators. Even for a gravity theory, for Einstein gravity, we need linearized Einstein gravity, we need to know how to calculate propagators. So that is, and in order to calculate propagator, which is a 2-point generating function, 2-point correlation function, we need to know the generating functional. Differentiating this generating functional with respect to the external source twice, setting the result to j is equal to 0 will give rise to the correlation 2-point correlation function, which is the propagator in quantum field theory. So let me stop here. Thank you very much.
Thank you very much, Sunandan, for another great lecture. Thank you. And I see there are lots of claps coming up from the screen. We have a question by Gary Kemp, and I just gave him the permission to ask the person. So Gary, please, sir, you already unmuted yourself. You're welcome to ask your question, please.
Yes.
Hi, everyone. Thank you very much for the wonderful lecture and also the previous weeks. They were very, very good. So something I'm not sure about. So when we were calculating the generating function, the generating functional for just in the quantum mechanics setting, we had these integrals that we were calculating, and then we did this small little rotation of the time axis, and that allowed us to isolate the ground state. So that's fine. But now I'm a little bit not sure. So, and I ask out of ignorance, does delta, that little, this parameter, this delta, does that not appear somewhere in our expressions? And, did we not maybe take the limit as delta goes to 0 at the end of the calculation? Because, on the one side, we take t and t prime to infinity times e to the minus I delta, that's fine. But then on the other side of the equation, there was just, the integrals from minus infinity to infinity, and delta seemed to kind of fall out of the calculation completely. And I understand that, with e going to infinity, all these higher terms were exponentially damped. So these are my questions.
Okay. Thank you for your question, and it is a very nice question. Let me go back to this slide where I have actually calculated this expression by, so we were after this object, after this object. This was the object that we were after, which is the overlap of this with this in the presence of the external source J. And this object, we wrote it in this form by introducing some identity operators. And then what we need to calculate now is this object and this object. So we have managed to calculate those objects very simply. And if we plug in all the expressions here, the result for this particular object, which we are after, is basically equal to this. This is the thing. And this is the point where we take the limit capital T prime to be equal to infinity e to the power of minus I delta. So this is the thing that we do here. So now let me just actually, it would have been nice if I had a blackboard, a big board here, but I shall try to write it over here. So if you notice, I shall write it so I hope you can it is visible. So just let us concentrate on this term. So I will write it in a very write it small. So it is e to the power of minus I by h bar, and let us concentrate on this term only, on this particular term only. So it is e to the power of minus I by h bar em t prime. So this is the term. And similarly, you also have a term involving t, and we want to take limits of this term. So let us see what happens. So this is equal to, I have very little space, so let me write this as e to the power of minus I by I by h bar em, and t prime is now infinity. So let me put infinity over here. So this is quite, so I'm actually doing quite sloppy things. I'm working with dangerous things, because infinity, I should not work with infinity. So I'm writing infinity, but you should be you should just take this in a it is not very rigorous, but it will do the job. It will serve the purpose. So if you
Yes.
see carefully that I'm setting capital T prime to be equal to infinity e to the power of minus I delta. But now e to the power of minus I delta, I can write this as cos delta minus I sine delta. So this I can write. And
Yes.
now this term I have already mentioned that if you look at this here, the delta lies between it is less than or equal to pi by 2. So that is the rotation, weak rotation, so to say, that I have carried out. So let me come here now. So this, the first term, it is e to the power of minus I by h bar em. So this is my em times infinity cos delta. So delta is a real, it is less than or equal to pi by 2. So the first term, this you can write it down at e to the power of minus I by h bar em. I hope you can see it on the slide, right? Is it
Yes, we can
visible?
see. Thank you.
Okay. Thank you. So this times e to the power of, let me write down the next term. It is, if you look at here carefully, so you have a minus of I and a minus of I. So if you multiply both these things out, what you will get is, it will be minus 1 by h bar em infinity sine of delta. So this is what we shall get.
Yep.
So now you can see that the first term, this is a product of this term times this term that we have. This is an oscillatory term. So let us forget about this term. The term which is important is this one. This is the term which is important. So this term, what will happen is the following. This term basically, so now there is also a summation over m. So when you expand the sum, it will be 1 by h bar e naught infinity sine delta. So you have a sum over m. Let me just go back. So there is a summation over m. There is a summation over m sitting outside. So if you expand this thing, so it will be this term. This will be the first term, and then plus e to the power of, I'm not writing the other terms obviously, but then it will be something like this, and so on, right?
Yes.
I've just expanded. Now, if we look carefully at this expression, and this is obviously multiplied by some other terms also. Now, if you look at this term very carefully, you will see that E1 and E2 and so on, whatever the other terms are, those involves E1, E2 and so on, they're greater than this E naught, because E naught is the ground state energy, right?
Right.
So
Yes.
E naught is the ground state energy. So these are damping terms. This is e to the power of minus 1 by h bar e1 infinity sine delta. So all this is a positive quantity, and so there is a minus sitting in front. So these are damping terms, and e1 is greater than e naught, e2 is greater than obviously e1, and therefore obviously greater than e naught. Therefore all these terms damp out are smaller than this term. You
Yes.
agree?
Yes.
So in this way, what we have managed to do by rotating this time axis in the clockwise direction is that we have isolated the ground state. This is the first thing that we have managed to do. And now what I'm saying is that once you have managed to do that, you again write this e to the power of minus 1 by h bar e naught infinity. You just forget about this sine delta for the time being. You put delta to be equal to pi by 2. Let this delta be equal to pi by 2. Then what will happen to this delta? This will become sine pi by 2. So this is 1. And you just replace this infinity by t prime. So that is the thing that has happened here. So that actually isolates all the ground states. So this limit is basically a sort of a mathematical way, or you can think it in a physical way of rotating the time axis in the clockwise direction. This procedure actually gets rid of all the higher energy eigenvalues. It basically gets rid of the sums. It only takes into account the m is equal to 0 value of the sum. So now you have come down. This procedure has let us to work with only the ground state energy eigenvalue. So once you have isolated this, now you put delta to be equal to pi by 2. So this was your question, that why is the delta not featuring in the calculation? Because you can set delta to be equal to pi by 2. So it is so sine pi by 2, that is equal to 1, and cos pi by 2, that is equal to 0. So this exponent, this full object is equal to 1, and therefore you have this e to the power of minus 1 by h bar e naught infinity. Now you just, once you have isolated this, you can again back weak rotate it. You can back weak rotate and come back to the original time axis, and you can write this to be equal to this.
I see. Okay. So you do the rotation, the terms get exponentially damped. You can even put delta equal to pi by 2, and then you have your results, and then you rotate back again.
Yes. What I would suggest is that I have actually provided all these steps. If you just once again work out this step carefully, then in a sheet of paper, then it will be very clear. If you just take the limit yourself, it will be very clear.
Thank you very much.
Okay, thanks.
Thank you. Thank you, Gary, for the question, and thank you, Sunandan, for the detailed answer. Are there further questions from the participants? I see there is no question in the Q&A. Here comes another question. Hector, please, you are happy to unmute yourself and ask your question.
Okay, thank you, Carl. I just wanted to know, with the structure of the source, when you introduced it in the action in order to eventually get to a generating function, is that the only kind of generalization, because the source is only multiplied by, I think it's a field or position? I think it was just Q of t. Are there other forms that you can introduce?
This is the standard form that is used in quantum field theory. So if you look at this slide, where we have written quantum field theory z functional of j, you will see that this is a path integral over the field phi e to the power of I by h bar. This is the action in the absence of the source, which is this, plus an integral over jx phi x d4x. So this is the standard form. So this is said to be the generating functional in the presence of the source, external source j. Why is this done? This is sort of a mathematical trick, because you want to extract the correlation functions from this generating functional by functionally differentiating this object with respect to the external source. So once you functionally differentiating this z of j with respect to the external source j, all these factors of phi, keep coming down in the integrand. So when you differentiate this with respect to j, it pulls off this phi factor from this exponent and it puts it in the integrand. And therefore, now it becomes an expectation value of that particular object. So this is a sort of a mathematical trick of the reason for introducing the external source is like a mathematical trick to extract the correlation functions. And this is the standard way in which it is done. There is no other way.
So you could kind of call this you're integrating in degrees of freedom, essentially.
Yes, you can think of it in that way. But this is sort of an object which helps you to calculate the correlation functions in the path integral formalism.
Okay, thank you.
Thanks.
Yeah, thank you very much, Hector, for the question. If there are no more questions, and I don't see any further raised hands or questions or comments in the chat, then Sunandan, thank you very much again for another great lecture. I see there again lots of clapping hands.
Thanks.
Swimming up the screen. Yeah, so thank you very much. Thank you very much again to all the participants.